Um, Thank you. I'm glad to be here. I'm also happy to follow Spencer, the last talk, which was an excellent talk. That part's a little intimidating, but I think you could take this as a kind of personal version, if you want, of some of the same issues that he touched on. Also, I now use this picture to introduce my talks because I hope you'll buy my book. You don't have to read it, but it would be appreciated if you would buy it. Now, El Niño should go back. El Niño refers now to a warming of the Pacific, but of course the reason people care about it and that it gets into interdisciplinary kind of issues is that it has impacts. And so this is in Botswana from the 82-83 El Niño. There's a drought. There's typically a drought in southern Africa. The drought's in Australia. Floods in parts of Ecuador, which wiped out infrastructure. Again, you might take these if there's a lot of interest right now in extreme events associated with climate change. And there are lots of examples of extreme events in the past climate record, not all of which are associated with El Niño, but that is one systematic global organizer of extreme events. This is California, which is hit by storms, and the top pictures are in Indonesia. In Indonesia, in both the 82-83 and this is 97-98, there were enormous forest fires in Kalimantan, which probably burned down as much rainforest or more as is typically cleared in the Amazon. This is a natural event, but it is aided by the people in these areas who wish to burn down the forests in order to replace them with cash crops. Okay, it's just a great opportunity when nature's going to favor them. In Peru, in coastal Peru, where it's usually extremely dry, this is 97-98, it created a kind of artificial drought, and the picture on the bottom is Fujimori, who was then the president of Peru, running around stocking the lake with fish, so that this is going to be a temporary lake, but one of the interesting aspects was his response he responded to this El Niño event, which was predicted by essentially running around the country kind of trying to clean things up and showing a presence, and it had some impact on political situation in Peru. I won't get into that here. Okay, what I am going to get into is a series of my own connections to various things that might be called interdisciplinary. One was prediction, one involves agriculture, one involves what some news writer called ethnoclimatology. One is work with Jeff on hydrology and vector-borne disease, and some recent work on El Niño and civil conflict. I felt a little funny when I realized that I've got 5 papers listed up here, 4 of which were published in Nature, none of which were published in the journal put out by the people whose building we are being hosted by. But then I remembered that 2 of those papers had been rejected by Science First. So I felt better about it. Okay. And my friend Ellie Zipperman says, you haven't done anything really important unless it's been rejected by Science or Nature. Of these papers, one of the secrets is to, it's actually very difficult, at least for me, to cover very many disciplines, and it helps to have students who may not themselves be initially experts in those other disciplines, but they're more flexible than I am, and better able to learn new things. And I think every one of these papers relies on that. Let me go now to prediction, and this is a paper that was published in Nature in 1986. It was preceded by, and it's about prediction of El Niño, and I'll come to that. But it was preceded by another paper that was published in Science, so I thought I'd get that in on theory, modeling, and simulation of El Nino. This was essentially the first published work that used the dynamical model to show that you could simulate El Nino, and then in some sense one could say we understand it. I want to acknowledge that this was work done, of course, against the background of other scientific work, particularly ideas that came from Jacob Bjerknes and Klaus Wertke, and also Jim O'Brien, who's in the audience, because there's a paper by Busalaki and O'Brien, which I consider to me is the single most important numerical experiment in physical oceanography. But it's something, in order to proceed into something, you kind of need to have some kind of confidence it's going to work, and the Busalaki-O'Brien paper, I'd say, gave me that. Anyway, the only point here I want to make for now is that we had a model, and as it shows on the top, it simulated something that wiggled with about a 4-year period, but irregularly, and that looks like El Nino. And on the bottom, and this is important, it had a spatial pattern that also looked like El Nino. And so one could argue that it was indeed had something to do with El Nino, and out of this came a number of theories. But the thing I wanted to talk about most was what we did in the next year, which was to make an actual prediction. And this was published in Nature. Okay, the picture on the bottom, by the way, you can see this is old enough so that we still, I don't know how this works, doesn't matter. It's old enough so they still colored it in by hand, okay? Something I miss because it was so therapeutic to do that sort of thing. And then I could get my children to help. That was nice too. Now it's, all right. You lose things with technology. But the picture on the bottom was published in Nature in sometime in the June, I think. And the picture on the top, of course, didn't come to be until later in the year. And a couple of things about this work. First of all, it was interdisciplinary at the time, which meant that it combined atmospheric science or meteorology and physical oceanography, which were then very distinct disciplines. Spencer touched on this a little bit. Part of it was, in fact, the style. Oceanography was a thing done by big bearded guys wearing boots. That's not my quote, that's Carl Winch's. And meteorology was done actually largely, as I knew it, largely by people who didn't go out and gather data, but had it come because there was a network of weather stations around the world they could rely on. And indeed, these modes of data gathering and the kind of limitations of what it was then possible to do in the ocean made for two very different cultures, and it was actually difficult to bring these things two together. And I can't say there was, at this point, terribly much reward for people who tried to do that, or in this case did that. The other thing that is difficult is that I don't know, this is eroded a bit because of climate change and the threat of climate change, but it was felt back then that the gold standard of what scientists tried to do was achieve understanding, okay? So working on prediction was a less noble undertaking, okay? I think it helped me that my advisor was Jewel Charney, who was not only an outstanding theoretical meteorologist, but was involved in the first numerical weather forecasts. Okay, so another thing I want to say is, so we did this. This was an actual prediction. It was published ahead. It got a lot of attention from colleagues, much of it fairly negative because they felt you shouldn't go public. You shouldn't actually have anything to do with the public was a pretty largely prevailing view, but you certainly shouldn't go public with such a thing. The interesting thing, in a way, in terms of acceptance of ideas and so on, which is part of what this is about, acceptance of interdisciplinary ideas, but in any case, this work really wasn't accepted then. It was what I think led to acceptance of the notion that we actually could perhaps predict this bit of climate variability was our ability to forecast our actually successful forecast of the 1991-92 El Nino event, because in early 1990 there had been changes in the southern oscillation in the pressure systems in the Pacific, and there's a whole bunch of people who said, look at it go, there's going to be an El Nino, and this would be at the end of 1990. And our model at that time said, no, it's going to hold off for another year, and that's what happened. And I think the fact that helped gain acceptance, despite the fact that there had actually been a successful forecast 5 years earlier. So one thing to keep in mind in terms of the possibilities, let's call them, of fostering interdisciplinary or any sort of change is that minds are just slow to change, and there's a time scale for that it's very hard to speed up very much, okay? And those of us as smart and as driven by data as we would take ourselves to be, but we also cherish our skepticism. So I don't think we change all that easily either, okay? Now going back to this, one of the issues that comes up then, and comes up again, of course, in spades for anthropogenic climate changes. So you make a forecast, now what? And when we made this forecast, when we had this forecast in 1980, starting in 1985, you begin to say to yourself, well, do I go public with this? This is, remember, 3 or 4 years, 3 years really, after the 1982-1983 El Nino. I showed you pictures. I mean, there was a lot of global devastation in many parts of the globe. It was to say that another El Nino was coming would be clearly be a scary thing for people, and so maybe you don't want to do that. On the other hand, if you know it's coming and there are things that people could do to get ready for it, should you withhold that kind of information? So that's one set of issues. The second set of issues is, how do you communicate this in a way that people will respond to? Now, to some extent back then, I would say I had a fairly naive notion, the sort of if you build it, they will come idea. You just put the information out there, and of course, because we think it's good information, people will do something with it. Okay, that doesn't work either, and the reality of the need to find a way of disseminating this information that would be effective led to, among other things, the founding of an international research institute now called for Climate and Society. And one of the, well, not one of, but in a sense, the key idea here is to help people understand ways in which climate affects their communities, and that involves more than prediction. It also involves an analysis of what climate variability is in reality, okay, in order to help them to plan and adapt, okay. And unfortunately, or in any case, the need for adaptation right now is, of course, inevitable, since it's abundantly clear that the globe, we're not going to do anything about anthropogenic climate change in time to ward off the need for adaptation. So we better get on with it. And there is experience in the IRI and a few other places in how to do this based on responding to natural climate variability, and so is the biggest signal we experience of that sort, since we don't live through the ice ages, except vicariously if you are a paleoclimate scientist. By the way, I've done some of that too. I've left that out of this talk. Sorry about that for some people. Okay, so that's what the IRI was set up to do, and rather than go through the words, if I can get this to advance, which I can now, just some examples I think are more telling. One kind of example of work done there is to study the role that dust plays in outbreaks of and epidemics of meningitis in the Sahel. Meningitis is a major difficulty, okay? In a lot of people are very excited about what's called index insurance. Basically, one of the adaptations to climate, the uncertainties of climate, is to buy insurance, but it's not really possible for small farmers in Africa, let's say, to do this. The costs are too high, and there's a kind of insurance where essentially it pays off based on whether some climatic index, which in many cases can be monitored remotely, exceeds some threshold. So it makes it possible to sell relatively, cheap enough insurance so that a poor farmer in Ethiopia can afford to buy it. Okay, that's something they're working on. In Indonesia, I showed that example from 97, 98, but forest fires are a problem, and the IRI has been working with local people there to do it. So this is an institution which I should mention was partly the foresight of NOAA, and in particular the most creative bureaucrat, if that isn't an oxymoron, that I've ever known, Mike Hall, put together. And I should mention, though, that what's happening now is NOAA has decided to stop funding this work. So it's this kind of, the experience and the capacity that's been built to do this sort of interdisciplinary work that's applicable to climate change is going to go away. Another fruit of this, just to mention, is because some of the students in the program are here, I think, is out of this work in the IRI, I founded a program that's now in its 7th year, which gives a master's degree called Climate and Society, and it's essentially a combination of climate science and policy and other, let's call them non-physical science aspects. And this has worked very well. The students like it, and by and large, they get jobs. I'd say one reason they get jobs is that this is a master's level program. They go into NGOs, they go into the private sector. They don't have, where things, I think, move faster than they tend to in academia in terms of adapting to new ways. Come back to that point later. Okay, next thing, El Niño and agriculture. So I was at a meeting on famine early warning systems in Africa. Now, the meeting was organized by Mickey Glantz. Some of you know Mickey Glantz. Mickey Glantz, I think, if there is a father or a grandfather of kind of climate and policy studies, it has to be Mickey, who started doing this kind of thing in the 1970s when he was about the only one. And he's done some terrific stuff over the years. And I have to say, of all the meetings I've been to in my career, and there are lots and lots of them, the ones that Mickey organizes are by far the best. Because he really knows how to get people across disciplines to talk to each other in meaningful ways. And one of the things is to get people to focus on what the question is, what the problem is, and not on the arcane issues of their discipline. Anyway, someone put up the red curve at this meeting. This is, when was it? It was, late 80s or circa 1990. It was a meeting on famine early warning systems in Africa, so it was held in Budapest. And they put up the red curve, and I said, I can predict that, okay? And they said, no, you can't, because, and they gave me all the reasons why you wouldn't be able to do it, and indeed I still know almost nothing about agriculture. And if you actually read up on what it takes to get a corn plant to come and turn into an ear of corn, okay, it does seem virtually impossible that so many things have to go right that it really can't happen. And in between two, we went from Rhodesia to Zimbabwe somewhere in the middle of this period, and practices changed and so on. So there were all these reasons why it shouldn't work, but yet I knew what the other curve, which is an El Niño index, looked like, and I knew that these things were the same. And indeed, if you plot them together, this is what they look like. And one of the things that is implied by that is one could predict, go to the top panel, you could predict fairly well what would be likely to happen, the dangers of drought in Zimbabwe, fairly far in advance, and could predict maize yield with a decent correlation. And if you came right up to just before the beginning of the planting season, say, which is in October, but in September, you could do, in fact, almost as well as the data correlation. I mean, this is very simple, okay? This is really simple in the sense of it's taking one curve of maize yield, which at the time I didn't know where they got the data from, and at this point I no longer remember where they got the data from. But anyway, they had the data, and we had, this, and they're just putting these things together. So one message is, I thought this was a nice piece of interdisciplinary science, but some people felt it was too simple. Okay. One further lesson about this is, so you could have predicted, put it over there, the consequences, or at least expected that there might be bad consequences from the 91-92 El Nino, which was quite predictable. That's the one I showed you earlier. It was well predicted, and taken necessary precautions. Instead, what happened in early in 91 was that the World Bank put pressure on Zimbabwe and other countries to sell down food reserves, in advance of what turned out to be a bad harvest season. Now, on the other hand, it gets tricky because when the 1997-98 El Nino was predicted, and it was going to be a big one, banks in Zimbabwe stopped loaning money to farmers, okay, who didn't plant. Turned out that it wasn't all that bad a rainy season for reasons that, speak to some extent to the limitations of our understanding of how to translate things as gross as El Nino, let alone climate change, into more specific local responses. But in any case, there's an interesting lesson here for the relation between climate and policy that really needs more attention. It's quite a complicated thing. Okay. This next example I have comes a little bit later. Was published in 2000. It's what a reporter dubbed ethnoclimatology, and it's a study of indigenous methods of forecasting. Involves pulling in an anthropologist, and it begins, but this is a picture in Peru of the terraced, sort of terraced planting systems that they have in some places. It's the cover of an American scientist who wrote an article in there, which I recommend over the version in Nature because it has much nicer color pictures, some of which are here. The bottom picture are potatoes, which is the main crop there, but they have many varieties of potatoes, far more colorful than what we typically see in our supermarkets. In any case, the origins of this work were, I was at a meeting in Peru and we went into the Altiplano and we're riding around in this VW bus, which really couldn't quite handle the altitude. And so we had to rest every now and again. And at one of these stops, the guide we had, Barbara Dikile, told me about a farmer who went and looked in the sky on June 23rd, the winter solstice, basically, and he looked in the sky at a constellation called Colloquia, and said, if the head is clear, this is June 23rd, and they look in the middle of the night, okay, then the rains will begin early in September, and if it's not, then the rains will hold off until later, and it'll be a bad year, okay. So I thought, this is really cool. They're making a climate forecast, a season to 6 months ahead, however you want to count it, okay? And I thought, well, This is a place where there's drought in the I mean, it rains in the coastal Peru, but in the Altiplano there's drought, okay, in an El Nino year. So I thought maybe it has something to do with El Nino, although exactly what it would be early in June was not terribly clear. Now, it turns out, and we didn't know this until quite a bit later, this forecasting method probably goes back to before the Spanish arrived, and who knows how much longer than that. But it turns out that the Colca, which means storehouse in Quechua, is the Pleiades, the seven sisters. Okay, and they look at the heliacal rising, where it rises near the sun. Okay, and basically you can see in these pictures the difference between big and bright and small and dim. You know, again, this method is ancient and is pretty widespread in the Altiplano. Okay. And when we wrote this paper, so I had an anthropologist named Ben Orloff who had actually done a lot of work in this region and wrote a beautiful book called Lines in the Water, which is a wonderful read, but also a student named John Chang, who is the one who saved us, because we sent this thing out and we said, it's cloudy, and that's why in an El Nino year there's more cloud cover, and that's why the stars are dim. And one of the reviewers, who was an astronomer, wrote the review and said, if it's really cloudy, you won't see a thing. Okay, so that can't be it. And besides, these people have vitamin A deficiency and they have bad eyesight. Okay, and the part of it that actually gets me is if they go up there for one night, okay, only, and everybody sits around drinking a lot of chicha, which is a beer made from corn liquor, and okay, how accurate a forecast could this possibly be? Okay, there's one guy who makes the call, who, you know, they have a sort of village elder or something, and I never, anyway. Okay, and what John came up with as the solution to our problem was subvisual clouds. So we got this wind scanning satellite data, and you could make the case that indeed there were subvisual clouds which would dim these things but not be so bad as to knock them out. And there is indeed an El Nino signal in the subvisual clouds, and there's an El Nino signal in potato harvests and so on. So, you know, it all kind of works. And one of on the anthropological side, Ben gathered the data from various studies, because we certainly didn't have any money to support any of this, from a set of villages in Peru, in the Altiplano in Peru and Bolivia. And most of them there are different variants of exactly what they're looking at, but they all come down to some version of bright or dim, okay? The interesting thing is that, in fact, okay, this information, these climate forecasts, which have a many-century history, do influence what they do, and they do adjust the planting times in accord with what the forecasts are. Okay, and there's a lot of things about this that might be pursued, but to me, one of the interesting ones is what lessons do they hold about climate forecasting now, and in particular about how people, especially in villages in the developing world, go about making decisions about what they're going to do, because they, in fact, Ben has actually pursued this in Africa, in Aboriginal societies in Australia, and most typically people make they have group mechanisms, social mechanisms for making decisions. And at Columbia, there's, well, it's more than Columbia, but it's housed at Columbia. There's a center for research on environmental decision-making, which involves a lot of anthropologists, psychologists, who are studying this not just in this culture, but in the ones that we think of as more advanced, like our own. Okay, but I think there's a lot of relevance to this that hasn't been, there's just a lot more that can be done beside the fact that it's just interesting. Okay. If you have any questions about this next bit, ask Jeff. Okay, I'm going to condense it down. I'll go back. Jeff was my student. I once made a remark that, because I'd read somewhere that like mosquitoes could breed in cattle hoof prints, and I didn't think that this was the sort of thing that most hydrologists were all that interested in predicting or had thought about predicting, okay? And yet that would be something you'd want to know, so we set out to try to do some work involving hydrology, and we were most interested in malaria, but we couldn't get any money for that because we didn't, well, anyway. We weren't interdisciplinary enough. I'll just leave it at that. So instead, we ended up doing studies in the US where the data is easier to come by and you don't need as much money to get yourself going. And one of the more interesting, this was the time of a West Nile virus scare, so we actually, the first study involved places in New Jersey where there was good data we could get, but the most interesting study, I think, involved St. Louis encephalitis in Florida, and the basic idea is this. In a few words, if you have temperature and precip, you can kind of downscale to get measures of soil wetness. That affects mosquitoes, and that affects disease. The mosquitoes are the disease vector, so that affects the occurrence of disease. And the tie-in to El Niño is the fact that much of the forecast skill for Florida, the season ahead, derives from an El Niño signal, which is quite strong there. So you go from El Niño to some kind of forecast of meteorological variables, temperature and precip to Florida, to soil moisture modeling, that's to there, and then to mosquitoes and disease. And one of the things I found kind of neat that came out of this was the notion that when you have drought in the spring, it restricts everything, the vectors, the mosquitoes and the birds who are the hosts, to essentially all being in the same relatively restricted number of places, and then when things get better again, they can disperse and initiate the early transmission phases of this cycle and begin to affect human populations as well as sentinel chickens. Okay. I never really learned much epidemiology, but Jeff did. Okay. Okay, the final thing I want to talk about is work that's ongoing now on El Niño and civil conflict, and this work is really more than the others driven by two students, Saul Zheng and Kyle Mang, who are we have a PhD program in sustainable development, it's called, but essentially these people are trained to be kind of economists, but they also learn a lot of physical science. So Saul, for example, has written papers on measures of tropical cyclone intensity that have nothing to do with economics or good, climate science, I would say. But in any case, this is an attempt to train people who are interdisciplinary, and I would make a distinction here, I think, between setting up an institute where you bring different people together and actually trying to create people like Jeff or Saul or say who know more than one thing. And there's a particular set of issues in doing that I'll probably try to touch on at the end. Okay, now the obvious subtext in talking about climate, anything about climate and civil conflict is, will anthropogenic climate change induce more civil conflicts, induce more wars? Okay. It's hard, it would be, in a sense, a beautiful goal to have a conflict module in a Earth system model like the one that Ron was describing earlier, but we're not there yet, and our notions of, well, there's the literature on war in this sense of what causes war is very interesting, but not, let's say, very conclusive right now, and not all that easy to turn into a quantitative model. Anyway, in attacking this subject and thinking that you're really interested in future climate change, you can try by saying, okay, there's something holistic about climate change. I'd like to look at changes over long time variations. Okay, but basically the real data sets on conflict start around the late 40s or 50s. And in any case, as soon as you go to long time scales, you have very few realizations of whatever climate variations. And you also have the problem that there are social and political changes and economic changes over all of those times that are going to confound any attempt to try to relate climate and conflict together. So that approach is kind of inherently limited. There's a lovely literature to read that on sort of climate, that relates climate and history and climate and conflict, like the books that Brian Fagan writes, which are, well, I like reading them anyway. But, in the end, as a scientist, you sort of say, yeah, maybe so. That could be, but it's certainly not a case that can be demonstrated that way. The other thing that's been done is to try to relate local temperature and precip to conflict, okay? And there's a couple of papers, most notably, I would say, by a group around Ted Miguel in Berkeley, but looking at these things, especially for Africa, where there's a lot of examples of conflict, unfortunately. But this has a couple of problems. One is it's critiqued on the grounds that these local events are not somehow, they don't scale up to global climate change. And so the inferences you're making from those we're not going, we won't accept. And the second set of issues, which is more technical, has to do with exactly how the data was handled. And as you can imagine, some of the difficulty is, what do you mean by a conflict? How do you, how do you code conflict into some database that we can all, think is a reasonable job? So some of these studies have been looked at in various ways, and there was a kind of news piece in Nature a while ago, if you want to sort of just spend half a page on what this particular debate about. Now, the El Niño Southern Oscillation Cycle is somewhere in between these things. It's global, okay? And it is not caused by anything social, political, or human. And it marches to its own drummer. It has its own time scale, and its time scale is not in any obvious way the time scale of socio-political variabilities, so that one can say that if there's any relationship between ENSO and civil conflict, it probably has something to do with ENSO. What it has to do with, we'll perhaps get back to. Okay, so this is the main result of this work. There's a lot of issues of what was done that I certainly couldn't take the time to explain, but we divided the world into countries that are affected by ENSO and those that are not. Okay, it's actually countries that are affected by a way where temperature increases and some other things follow, and countries that are not. There's a pretty good correlation between countries that are affected being in the tropics or low latitudes and other countries being in high latitudes, but it's not a perfect correlation, certainly. Okay. And if you then simply relate conflict risk, the risk, and again, measuring what is meant by conflict risk is another issue that's gone into in some detail here, but in the paper. But in any case, the bottom line is that in countries where there is an ENSO influence, the risk of conflict goes from around 3% in a La Niña year to something approaching 6% with a good-sized El Niño. So that's about a 3% swing over this range of climate variability. The average for these countries is around 4%. The weakly affected countries, this is a kind of verification. First of all, they don't show any El Niño signal, as they shouldn't, because there's no climate signal in these places. Okay, so well, I'll make another remark on that. There's no climate signal in these places from El Niño, so your first thought is, well, there shouldn't be you shouldn't see anything then if you just look for variability with El Niño. I will say that on the other hand, you might say, well, if El Niño has effects on global agricultural outputs, for example, which it does, then you might say, well, there could be price shocks in various places, even if they themselves are not directly affected by El Niño. So this is partly telling you that if there is such an effect, it's not very great. That has to do in part with making some estimate of how integrated markets actually are, and more things than we've had time to study. There's a lot more that can be done with this. Okay. One other kind of verification, since I'd say most people who see this tend not to believe it, especially if they're scientists. Okay. One kind of thing that is perhaps a bit of supporting, again, it doesn't prove much, but in some of these places, not many, you have outbreaks of conflict, of violence by month rather than just annually aggregated. And in those places, you can look at differences in monthly things. And what you see then is that the difference between El Niño years and La Niña years do tend to occur. The greater incidence of conflict in El Niño years does tend to occur later in the calendar year. And since El Niño peaks toward the end of the calendar year, that means basically, well, that's the way it should be. If they were somehow different in the early part of the year, you would have every right to be suspicious. There's something really funny going on. So this is kind of a consistency check, if you like. Okay. Now, it's no. Okay. One of the things that is well known to influence incidence of conflict is income, national income, okay? And so one issue is to see how that factors in together with climate. And what you see on the left, see if I can actually figure out which button makes this work. Ah, that one, okay. So here, all right, we plotted essentially the mean incidence of conflict in countries, and then just plotted as a function of per capita income. So that's $1,000 and $10,000. Okay, and as expected, these curves are such that the probability of conflict, of an outbreak of a conflict, civil conflict, decreases with income, with per capita income. And this is statistically the same in countries that are affected by El Niño and those that are not affected by El Niño. The kind of dependence on income is pretty much the same. Okay, and you get something a bit different. This is the factor that tells you to what extent are they influenced by El Niño, and this is again trying to see what that coefficient is as a function of income, okay, and it has, it's larger in countries that are poorer, okay. So there's no contradiction here between the well-known result, and it's what you'd expect. countries where income is lower are more vulnerable, and therefore more likely to be influenced by climate. And if you think of beta, as I've written it here, beta times Niño 3, this is a multiplicative effect. It's not a, it's quadratic. Of course, that's because we made the simplest model. It isn't really that way. But anyway, these two effects go together in the way you'd expect. Now, one of the things this allows you to do, if you like, and again, you may or may not like this way of thinking about it, I kind of do. If I say, okay, the risk of the difference between the probability of conflict in a La Nina year and an El Nino year in these places that are teleconnected is about 3%, okay? And I can translate that into how much would I have to raise the income in these countries to kind of, counteract that, okay? And the answer is by an order of magnitude, from $1,000 a year per capita to $10,000 a year, which strikes me as a sizable change, okay? This is not in other words, I would say that this El Nino effect is not a small effect relative to other kinds of things that influence conflict. Again, all of them taken together are perhaps still fall short of explaining as much of the variance in conflict as one might like. Okay, so first summary is, the basic point is that there is a signal that the El Nino Southern Oscillation cycle shows up not just in rainfall and agricultural output and all kinds of other things that are readily relatable to climate, but it also shows up in conflict. And in fact, for whatever reasons, this is another issue, the overall conflict, the mean conflict risk in countries affected by this climate variability, El Nino, is higher than it is in countries that are not so affected. But within those countries, there's a big change. And the second thing is it's in some sense comparable. And by one way of estimating it, we would say that about 20% of all the conflicts are related to ENSO. Now, it may be, and there's some statistically not quite significant hint of this in the data, it may be that it's not that the El Nino is making a conflict that wouldn't have happened. It might be advancing, it might be affecting the timing of it, okay? And there's some extent to which I think that's certainly likely, okay. Now, I don't think, so how does this work? Okay, well, I have an answer, but it's, there's not enough room in the margin of this notebook to to get the answer out. But you can ask about that if you wish. And what are the implications for 20th century climate change to come? That's kind of where we started. And I won't answer that in any more detail because I should have answered the first question than to make the following point, that one of the things that's come up on the agenda, the climate change agenda, is the issue of extreme events. And in fact, what's going to do the most damage, I think, are extreme events. If I think of ecosystems, for example, it could be like the combination of climate change and some extreme part of a natural cycle that will do the most damage. We have a problem with this somewhat in articulating to the public the fact that when there are hurricanes, tropical cyclones, we say, well, there's climate change could make these more likely, but you can't attribute it to any, we can't make a definite attribution of any particular event. Okay, so what I think is that there's that aspect, and then there's the fact that you can think of it in terms of sea level. Okay, sea level rises, but what's going to do the damage is going to be the kind of storm surges that occur already. It's just they're going to be a lot worse. So I think that's one implication anyway that I would be seems fairly reasonable to me. But to make more implications, you either have to extrapolate more than I'm going to do right at this minute, or get a better handle on what you think the mechanisms are. I don't know how I'm doing on time. But let me close by trying to address, since this is my slot, some of the motivations of this workshop. And I was thinking when I wrote this question down of what you say to younger people about this, okay? And it might, and one reason is it might be useful, and in fact, I think, and I don't think I need to belabor this point, but for some of the critical problems we face right now, that it's indispensable. And not only are these problems critical, but they're actually quite interesting. I mean, I thought, well, okay, it's fun. I mean, I like doing the stuff with agriculture and learning a little bit about how corn grows and how people who do agricultural economics think about things a little bit, and certainly the stuff in the Altiplano and so on. It's just fun, and so understanding something about civil conflicts would be fun too. Although it's very hard. On the other hand, you do it at your own risk. I forgot to mention, I said a lot of nice things about Mickey Glantz. Of course, one of the things that happened to Mickey Glantz, the dean of interdisciplinary climate social science studies, the guy who should be the exemplar, he got laid off by NCAR. Okay, you could say that's not because he did interdisciplinary work, but I think actually in a certain sense it is. Okay, so I think you all should do this because it's important and it's fun, but at your own risk. How to foster it? Well, okay, there's the old-fashioned way, if possible. This probably works the best, okay? You throw money at it. Doesn't necessarily work well if you throw the money at it foolishly, but if you think about doing it intelligently, it's a good idea. Another thing in terms of academic, getting a department to hire somebody who does something interdisciplinary rather than my pet thing at the moment from my department is, we really need, they'll tell me, a metamorphic petrologist. And, okay, I have nothing really, I used to have nothing against metamorphic petrologists until I heard this too often. But, and my department's pretty open relative to many others, I'd say. Okay, so that's, time is a James Brown lyric, money won't change you, but time will take you on. Okay. And one thing which may be a little bit different is when you get into something interdisciplinary like climate and agriculture, the first things you do, it seems to me, the first things you should do are not terribly sophisticated, okay? They're pretty straightforward. And if I work, as I have a little bit, on what determines the latitude, the location of storm tracks in the atmosphere, this is an incredibly esoteric literature that involves some really high-class geophysical fluid dynamics, okay? And also, I don't know that well, anyway. It's a really hard problem, very interesting, very intricate, and very hard to explain to more than a handful of people what's actually going on. But something like relation between climate and agriculture, let's say, is pretty simple. If you do good work on that, it's going to be relative to some of this other stuff, it's likely to be technically unsophisticated. I mean, if you're brilliant enough, you're brilliant, and you do something, mind-blowing, fine. But most of us are not that brilliant, okay? And it's hard to count on that. So, I think that if the system would somehow reward taste in problems a little bit more than it does, rather than this kind of sophistication, it would help. I don't know how you make that happen exactly. I'm done.